Good morning. So last class we have seen about the Indian nuclear power scenario. So how the nuclear power is being started in India. So what are the reactors in which we have tested, and how far we are lagging from other developed countries. Like that we have seen. So today we are going to see about the technology behind the nuclear power plant. Yeah. So if you see the main working principle of nuclear power plant, so a nuclear power plant works in a similar way as like a thermal power plant. So if you know the thermal power plant, then I think 70% of your nuclear power plant is over. The only thing is that reactor we are adding over here, and also fuel. There we use the like a coal as a fuel for heating the water. So here we are using the nuclear fission materials for heating the water. That is the only difference. Otherwise, the construction wise, everything is same. The only thing is that reactor, that coal handling plant, ash handling plant will not be there. So instead of that, reactor will be there. That reactor, from that reactor, enormous amount of heat or energy will be produced. That heat might be used for heating your water. Then the same procedure, how it is being generated, like that we are going to see. So next, inside the nuclear power station, energy is released by the nuclear fission in the core of the reactor. So reactor is, I have in the last class I have shown one picture. So how the reactor where it is being placed in the nuclear power station, like one dome shaped structure will be there. Inside that only, they will be keeping that reactor. So to avoid the any so any accident, any leakages happening means it can easily protect, and simply like that they will close. If any leakages happen, they will simply close that particular the whole reactor itself. They will go for a constructing new reactor or backup reactors, backup structures they will be using for generating the power. So if you see here, the main thing, the main material what we are using in like nuclear power plant is uranium 235. So here 1 kilogram of uranium 235 can produce as much energy as burning of 4,500 tons of high grade variety of coal, or 2,000 tons of oil. Excuse me. So 4,500 tons of high grade coal. So that is equivalent to 1 kilogram. Normal 1 kilogram of uranium 235 is equivalent to 4,000. But imagine for carrying the 4,500 tons of coal, how much transportation cost is needed, how many workers are working behind to keep that is to store that coal in coal handling plant. That is a very tedious process. It is very costly also, the maintenance and transportation. Today, you know, the cost of diesel and petrol prices. So that is very costly. So 4,500 tons of high grade coal is equivalent to 1 kilogram. So if you have 1 kilogram of uranium 235 in your hand, then that will be equivalent to 4,500 tons of coal, high grade coal, and 2,000 tons of oil. So this is the very big advantage of this nuclear power plant. Okay. So here what we are doing is uranium 235 is being bombarded. Okay, being bombarded. So if you see in this picture, neutrons also it is coming out. Protons also it is coming out. So if you see here, it is a chain reaction. So if you keep this is the starting, like, so that will create another one uranium-235. Again, and there it will be separated like protons, combining the protons and neutrons. So again, from that neutrons it is coming out, and again huge amount of energy is also coming out. So again, this chain reaction will keep on moving like this. Okay, so if you are seeing in this picture, no, this chain reaction is keep on moving like this. Okay, you can't even control this chain reaction. So that's why we are going for some moderator inside the reactor itself. Okay, so it is keep on, once it is being bombarded means we can't able to stop. So only with the help of moderator only we can stop this chain reaction. So that's why this is once say for example 1 kilogram of uranium 235, once it is being bombarded means it will be lasting up to 1 year. They will be using that nuclear fuel for more than 1 year. Because every time the chain reaction will keep on moving. Okay, so imagine this chain reaction is attacking our body, our human body in the sense. What it will happen is it will change our DNA. This chain reaction will go inside our skin or go inside our DNA. It will change our DNA. So even your age is 20, due to the fast reactions, fast moving reactions, what it will happen is your DNA will be growing, like your skin will be growing like anything. At the age of 60 years, how your skin will it will grow now. That much fast, even that 40 years remaining, that period is 40 years. So that 40 years period will comes in only 1 year. Even in a year, you'll get that 40 years. What are the changes you're doing? No, that is called cancer. Okay, cancer, fast growing of cells. You can't even control. So you have to go with the chemotherapy for cancer attack patients. So weekly once, what they will do is weekly once or monthly once, they will go for a chemo. What they are doing is they will simply inject the heat, and it will it will avoid that movement that is fast growing. That skin will be just they will be avoiding. So that's why we'll just keep on reducing that fast growing cells. So like our cancer also will be reducing like. So this is called nuclear chain reaction. Okay, so in this, uranium exists as an isotope in the form of U-235, which is unstable. So what is meant by isotope? What is meant by isotope? So isotopes are the variants of a particular chemical element which differs in neutron number and consequently in the nucleon number. Okay, so and if you see like so isotopes are a variants of a particular chemical element which differs in the neutron number and consequently in the nucleon number. All isotopes of given element have same number of protons but different number of neutrons in each atom. Okay, so that is called an isotope. That is, all isotope of a given element have which is having same number of protons but different number of neutrons in each atom. Okay, so that is called isotopes. Even in uranium-235 also same. It have same number of protons but different number of neutrons in the each atoms. When nucleus of the atom of a uranium split, the neutrons released hit the other atoms. Okay, neutrons released hit the other atoms and split them in turn. More energy is released in each time another atom splits. Okay, so more energy when atom is splitting, so more energy will be producing. That reaction is called chain reaction. Okay, So nucleus of an atom of uranium is split. In that, neutrons released hit the in that say for example, one neutrons will be released and hit the another atom and split in the turn. So more energy is released in each time another atom splits. This is called chain reaction. So that more energy, not only so more energy in the sense you can generate more amount of power. So more energy is directly proportional to power produced. So more energy is produced, power production also will be more. So less energy will be produced, power production will be reduced. So that is the thing. Yeah. So here in this picture, you're seeing. So this is the target nucleus. So neutron is hitting the other other atoms. So in this atom also splitting to one neutron and another fission product. Okay, and some neutrons and another fission products. In that fission product only, like your energy will be produced. Your energy will be produced. Yeah. Next, nuclear fission. Heavy nucleus split into two parts in order to become more stable. So if you see here, heavy nucleus split into two particles to become more stable. So it is split into this Kr92. Okay. So and barium 141 nucleus. So and also with some energy. Okay, with some energy. This uranium 235 is split into this two particles to become more stable. So these are the red color. Red color is the proton and green color is the neutron. So here also red color is the proton, green color is the neutron. Yeah, I think you already studied this in chemistry. I'm just recollecting this. It is a process of splitting up of nucleus of a fissionable material like uranium into two or more fragments which release the enormous amount of energy. That is called nuclear fission reaction. So in 2 marks, sometimes they will ask what is nuclear fission reaction. So nuclear fission reaction is nothing but a process of splitting up of nucleus of fissionable material, that is here uranium 235, that is into two or more fragments which release the enormous amount of energy. The nucleus of uranium 235 is bombarded with high energy neutrons. So high energy neutrons is being bombarded with uranium 235. So U235 plus 0N1, okay, which is being bombarded. It will gives barium 141 and this krypton 92 Kr92 plus 2.5 N1, that is neutrons, and 200 okay mega electrical volt of energy is being produced. 200 mega electrical volt energy is being produced. So one electrical volt is 1.6 into 10 to the power of minus 19 joules. That is 10 to the power of 6 electrical volts. Okay, so one mega electrical volt is 10 to the power of 6 electrical volts. So 200 means, so 200 into 10 to the power of 6. So that is nothing but 2 megawatt. Sorry, yeah, yeah, 2 megawatt of energy. Okay, 2 megawatt of energy is being produced in like a 200. So imagine due to the chain reaction, this will be like uranium 235 will be heating more amount of okay. So in each reaction, 1 to 2 megawatt, 2 megawatt, like that. If 100 reaction is happening in that particular nuclear reactor means, so this 2 into 100, so 200 megawatt. So 1000 means 2 into 1000, 2000 megawatt, 2000 megawatt. So like that, 400 means 4000 megawatt. So that much energy, that is megawatt of energy, is easily produced in this okay nuclear fission reaction. So here, if you see, uranium-235 is split into two fragments, that is barium-141 and krypton-92 of approximately equal size. So both are, you have seen in that picture also, both are in like equal size, and about 2.5 neutrons are released, and 1 neutron is used to sustain the chain reaction. So 1 neutron is sustained inside that particle itself for that chain reaction, and 2.5 neutrons is being released. We have seen in that chemical reaction formula is released. 0.9 neutron is absorbed by uranium-238 and becomes plutonium-239. Okay, 0.9 neutrons is absorbed by uranium-238 and becomes plutonium-239. The remaining 0.6 neutron escapes from the reactor. The neutrons produced move at a very high velocity of 1.5 into 10 to the power of 7 meter per second. So what is the speed of light? Light 3 into 10 to the power of 8 okay, meter per seconds. And that is the speed of light. So imagine it is half of the, that is 1.5. This is 1.5 into 10 to the power, like approximately half of the speed of the light. Okay, so that much fast it is hitting the other particles, and the fission other nucleus of uranium-235. Thus, the fission process and release the neutrons take place continuously throughout the remaining material. So it is hitting like, so imagine we have seen only one reaction. It is continuously hitting, and the chain reaction is forming anything. That chain reaction. So one simple example I will be telling. So have you watched that Indian film? In that the last climax scene, that one robot will create more robots, like that here also. So one particle of uranium-235 will create more chain reaction. So that is also in that film also, it will be showing like a chain reaction. So one robot, that chicky robot will produce more robots. So same like that here also, this uranium-235 will be after bombarding, it will that neutron is hitting another atoms, that is hitting another. So like that chain reaction will be more. So more amount of energy is being produced. So large amount of energy, that is 200 million electron volts. That is 200 million electron volts. So 200 million electron volt is produced. So 200 million means 200 into 10 to the power of 6. Okay, that is 200 megawatt. Okay, 200 megawatt, like that it is being produced. Like that in the nuclear power station also, some more okay, reactors will be there. So this is of 1 kilogram, that is of half kilogram, that is of some other 2 kilograms, like that they will be producing. So 1 kilogram means some approximately 200 megawatts. So another half kilogram means 100, like that. It will be changing that based on the like material and the kilogram of material, weight of the material, what we are changing. So that much power is also being produced. So these are the so before seeing the construction features, we'll see the general advantages. Then we'll come to this. Yeah. So what is a nuclear power station? We already seen a generating station in which So what is a nuclear power station? A generating station in which nuclear energy is converted into electrical energy. So what we are doing is we are converting the nuclear energy into electrical energy, that is nuclear to heat and heat to electrical energy. Electrical energy is known as nuclear power station. In nuclear power station, heavy elements like uranium-235 or thorium-232. This thorium only is easily available in our like a Bay of Bengal, okay, that region, thorium 232, are subjected to nuclear fission in a special apparatus is known as reactor. So this substance, what we are doing is subjected to nuclear fission. What we are doing is we are making that in that to nuclear fission in special apparatus. So that is called a reactor. So the heat energy thus released is utilizing and raising steam. So if heat is produced, automatically we can easily boil our water. So if we easily boil our water, means it will produce high that is superheated steam. That superheated steam is hitting a turbine and it will create the electrical energy. So that is coupled with an alternator, it will create the energy. So that's what they said here. So most important feature of nuclear power station is that huge amount of electrical energy can be produced from a relatively small amount of nuclear fuel as compared to other conventional types of power station. So instead of doing very like a coal handling plant, like doing very much of okay, that storing the coal and all that thing and all, not that here. Only very small amount, with a very small amount we can produce huge amount of electrical energy. It has been found that complete fission of 1 kilogram of uranium-235 can produce as much of energy produced by burning 4,500 tons of high-grade coal. Okay, although the recovery of principal nucleus, that is uranium and thorium, is difficult and expensive. Okay, if you want to buy that 1 kilogram of uranium 235, that is expensive, and also it has to come we are relying on USSR and the US, so it has to come from their own country to our own country. So very careful. It will be they will be it will be coming to our country. Very careful, because any simple leakages, small leakages happens, means that's it. The whole like 70% of nation is will be attacked with this this nuclear fission reaction. So that is why you have to be very careful. So that's what said here, and also expensive. Yet total energy content of estimated world reserve of these fuels are considerably higher than that of conventional fuel. So this fuel, that is already I said, the thorium reserves, but in our India, without with the thorium thorium 232. So what we have to do is we have to go for three-stage fast breeder reactor for producing this for producing the power. So that is that technology is being developed. That technology, and also they went for testing, and also commissioning is not happened. Okay, tested, keep on testing. 500 megawatt is keep on testing. And last October, October 2020, they plan to start again. Some due to some fault, again they are testing. So if that is over now, so we should not rely on like US technology or US technology. By own itself, we can produce the power, but safety is very important. So again and again, I'm repeatedly telling, because it should be happen in the apart from the human population. Okay, remote places, very remote places. Like that, it should be happen, and also safety is very important. At present, energy crisis, but one more thing also, that due to energy crisis, after 30 years, our coal resources will not be there. And after 40 years, our oil resources, we have to rely on new technology. Crude oil also will be slowly, it is reducing. And the like LPG gas is reduced also. After 60 years, 50 years, no gas resources will be there. So after that, after 50 years, we have to think technology with we have to produce the power also. In that time, the load might be of increase like 4 times, 5 times, 5 times. Why? Because the gadgets we are purchasing like anything nowadays. Okay, so then monthly we are getting two gadgets, two new appliances in our home. Like that, monthly we are getting. So imagine like after 60 years, how the whole so in India, like 1,86,000 megawatt is the total load. So after 60 years, it will be increasing like multiple. It will be multiplying like anything, like 3 times, 4 times, 5 lakh megawatt might be coming in the after 60 years. So we have to tackle that 5 lakh megawatt. 5 lakhs megawatt power production is not at all an easy task. So what we have to do is we have to rely on some other very new technology, and also less costly also. So we have to rely on this type of nuclear resource only. But even though in well-developed countries, they're generating like 8,000 megawatt, 10,000 megawatt like that. So in India, still, I think maximum we are producing around 6,000 megawatt only all over the whole India. 6,000 to 7,500 megawatt. It is somewhat, it will be varying. So 7,500 megawatt is maximum. So after that, we are not going for touching most of power production from this nuclear power plant. And if you see like energy crisis happens, means definitely we have to rely on this kind of nuclear technology one. So what are the main advantages? So main advantages is amount of fuel required is quite small. Amount of fuel required is quite small. That is 1 kilogram itself. You can produce like around 200 megawatt more than. Therefore, there is a considerable saving in cost of fuel transportation. So fuel transportation here is only very few, not that much, like 100%. If you take like nuclear coal, then 1% for nuclear. So very less cost is being for transportation. And a nuclear power plant requires less space compared to any other type of same size. Okay, so less space, only reactor. After that, so if you see like coal power plant, this coal handling plant, ash handling plant, then boil, then that furnace, that itself take like 60% of the whole space. After that, the generator, like that, cooling tower and all that. But this itself taking more space. So this nuclear power plant produces less space. And also, if you see like it has low running charges, as a small amount of fuel is used for producing bulk electrical energy. So running charges is very low. So running charges for thermal power plant is very more, as you know. Like you have to take that particular coal from coal handling plant to the furnace. So that the distance between that coal handling plant and furnace is approximately 0.5 kilometer to 1 kilometer. So 1 kilometer you need to travel. That coal has to travel. So if you see like thermal power plant, you'll be they'll be having some conveyor belts that will be going from coal handling plant to that boiler, that is furnace. So it will be traveling for 1 kilometer or more than that also in some other power. So that much running charges and all we can easily reduce in this nuclear power plant. And this type of plant is very economical for producing bulk electrical power. So economical, as I said. Next, it can be located near to load centers because it does not require large quantity of water and need not be near coal mines. Therefore, the cost of primary distribution is also reduced. So near to load centers we can keep, but the load centers should be in the remote places. Why? Because it will be in the domestical area. It will imagine some nuclear power plant is they are planning to construct inside our Hyderabad city or somewhat outskirts of Hyderabad city. So no one will allow. Our people also will not allow that power plant inside the city areas. And load centers you can keep, but that too so some with some safety precautions. With some safety precautions you can see. And there are large deposits of nuclear fuels available all over the world. Therefore, such plants can ensure continued supply of electrical energy for thousands of years. Okay, and one thing, and also while you go inside the nuclear, you have to keep that that fuel material. No, so what they will do is inside the nuclear power plant, they will be wearing some jackets. Okay, the jackets, entire the whole thing is the whole body will be closed. Like we are wearing for our like COVID, no, COVID we are wearing some dresses and all, like PPE kits and all we are wearing. Like that, that kits and all will be like it will resist the nuclear fission reaction. I think you have seen in that film also. That film also they will be wearing that jackets when they are entering into that nuclear fissile particle. While taking that fissile particle itself, they will be wearing all the like coats, mask, everything. So that is also the safety measures also, and it ensures reliability of the operation. So reliability of the supply you can get. Okay, you can go for 24/7 into like 24/7 weeks, and also 365 days you can produce the power whatever you needed. Only thing is that you have to get that fuel, how many kilograms you need for producing this much megawatt, that you need to get. Next, disadvantages. Disadvantages, if you see, like fuel used is expensive, that is expensive and difficult to recover. Okay, difficult to recover, and also capital cost on nuclear power plant is very high as compared to other power. So imagine if you want to construct a nuclear power plant of 4,000 megawatt. Today now we are living in 2021. So it will definitely take 5 years of time to construct, and erection and commissioning plant also will be taking more amount of time. 4 years, 5 years it will be taking, and also capital cost you need to spend on nuclear power plant is very high. So developing country will be rely on this. The capital cost is very high. So developed countries, they can easily construct, but developing country is which needs much time. So India is a now I can't say like a developing country, because recently, as per the Forbes okay survey, so we are the third richest country in the all over the world. So we are developed country, but the people living in India is still developing. I can't say like India is still it's a developing country. It is a developing country, but still the people only is trying to uh, developing. We are only trying to develop in our country, but India is a developed country. For corporates, it is a developed, but for people, it is a developing country. Okay. Next, the erection and commissioning of plant requires greater technical knowledge. So erection and commissioning of plant, so high skilled workers is needed. High skilled workers is needed. So like reactor construction and all, it needs high skilled work. And if you see like fission, the fission byproducts are generally radioactive and may cause dangerous amount of radioactive pollution. So after fission, that byproducts is there, like krypton and that barium particles and all that. So that particle are like byproducts. So that products we have to safely we have to go to a deep sea, and we have to dig a very huge pit and all. We have to safely close that fission byproduct. That is, if that fission also coming out now, again the species inside the sea also will be getting affected. So that is very carefully you have to take that radioactive pollution particles outside, and you have to safely you have to do the these things. So if this is not happening now, again it will be very harmful for human beings. Human beings, it will be very harmful. Okay, so that's what it is said here. The breaking of nuclei of heavy atoms into two nearly equal particles with release of huge amount of energy is known as nuclear fission. The release of huge amount of energy during the fission is due to mass defect. That is, mass of the final product comes out of the less than initial product. So the mass defect is converted into heat energy according to Einstein relation. So if the energy is produced, if some heat energy is produced, we can easily utilize that heat energy for boiling our water. After boiling our water, next we can produce the steam, superheated steam. Then we can produce the power energy. So that is according to Einstein relation. That is equal to mc square. And also maintenance charges. Maintenance charges are high due to lack of standardization. So maintenance charges is very high, as you know. Like moreover, high salaries of special trained personnel employed to handle the plant further to raise the cost. So high salaries is being given. So if you are also in future, if you are also getting placed in this kind of nuclear power plant, so you will get more than 2 lakhs or 3 lakhs per month. Okay, a normal assistant engineer who is working in nuclear power plant, if you see the scales, it will be like more than 2 lakhs per month. You'll be get. But imagine safety is very big question mark here. Okay, those who are working there, safety is very even you get more salaries, but once anything accident happen, then I don't want to say that. Next, nuclear power plant are not well suited for varying loads. Varying loads, as reactor does not respond to load fluctuation. Okay, so load due to the because that particular nuclear power plant is being constructed for only say for example 500 megawatt means 500 megawatt only. So due to the varying loads, you can't increase that to 1000 megawatt simply like 600 megawatt like that. So particularly if that power plant is producing 1000 megawatt means more than that you can't even produce. So only within that range only you can produce. So I'll be coming to your doubts later. Next, after end of this class, I'll be coming to your doubts. Next, the disposal of byproducts. The disposal of byproducts which are radioactive is a big problem. So byproducts, as I said, that is radioactive materials is a big problem. They have either to be disposed of in deep trench in a sea away from the seashore. Away from the seashore, they will be going nearly 20 to 30 kilometers inside deep seas, and there they will go for deep trench. Then they will be disposing all this nuclear byproducts. So that is also there in this nuclear power plant.